Good morning, guys. Hope everyone is doing well. Happy Tuesday. Welcome to a new week. Let's go ahead and talk about calculating KEQ and using KEQ in calculations. So we're going to start with a little practice problem here. Um, so we have this reaction, find the KEQ given the information. It says an analysis of the equilibrium mixture in a 1 liter flask at STP. Remember, STP means standard temperature and pressure. The only reason that's mentioned, along with the volume, is because temperature and pressure do matter for KEQ. But we don't need to use them in this calculation. Just understand that the KEQ would change if the temperature or the pressure changed. Okay, so we're given these concentrations of everything in the reaction. The first thing I want you to do is come up with the KEQ expression. So forget about numbers, forget about molarities, and just come up with the KEQ expression. Okay, so there you go. The 2 here on the NO, or first of all, remember it's products over reactants. That's an important point to make. The 2 here on the NO is because our first product has a coefficient of 2, so its concentration is going to be squared. Cl2 is just 1, and then on the other side, my reactants, the NClO is 2. So there's our equilibrium expression. So then the next step is going to be to plug in our concentrations and see if you can come up with the value for KEQ. I want you to remember that KEQ can range from very, very, very tiny to huge. So many, many thousands of times difference between KEQs. So don't freak out if your answer is really, really big or really, really small or kind of in the middle. Could be anything. Okay, so there you go. And I did this on my little phone calculator. So that's why I kind of wrote out, the numerator, the product of the numerator, and then also the denominator, and then divided, just to make sure I didn't make any mistakes. Yes, even the phone calculator has parentheses, so I could have probably done this all in one step, but just a little bit easier, mistake-free to do it this way, hopefully. So 7.8 is what I got. There's no unit on that. I didn't worry about units. With KEQ, don't worry about units because they would be different every time depending on whether you were squaring or cubing your molarities or taking them to the 10th power as even possible. So because the unit would kind of be different every time, sometimes it would be like 1/molar one time, the next time it would be molar squared, molar to the 4th. So we just leave out the unit with KEQ, and I also left it out here when I showed my work, which is okay. So 7.8, what does that mean? Does that mean the products or the reactants are favored? Okay, so you should have said that the products are favored by almost 8 times. So there's going to be a lot more product at equilibrium, which means if I go back to my reaction, there's going to be a lot more nitrogen monoxide and chlorine gas at equilibrium and a small amount of our reactant. Okay, so let's try another problem. This one's going to be very, very similar. So the equilibrium equation for the formation of ammonia is, there we go. So at 200 degrees, again, we're not going to actually punch the number 200 into our calculator, but it is important to understand that this value would be different if we had a different temperature. Our KEQ value, that is, would be different at a different temperature. Okay, so it gives you some equilibrium concentrations and wants you to find KEQ once again. And once again, let's go ahead and see if we can just first write the KEQ expression without the molarities. Okay, there we go. So you should have come up with something like that with my products on top. And again, to the 2nd power because there's a coefficient of 2 for my NH3. To the third power for the hydrogen because there's a coefficient there. But there's no coefficient in front of N2, so it's just 1. I do want to make a quick note, a little side note there. We mentioned this a little bit earlier, and it was mentioned in the CK12 reading. But remember that only gases and aqueous solutions go into KEQ expressions. Everything else essentially becomes 1. So if, for example, these 2 were liquids and you only had a gas here on my product side, it would just be the KEQ would be equal to the square of NH3 concentration. We're not going to really go through any examples like that just because I think that's pretty simple. We're just leaving stuff out. But let's go ahead and calculate the KEQ value. given these concentrations now that we know what the KEQ expression is. Okay, so there you go. So I just put in my molarities, NH3 on top. Remember to square and cube as is called for. Here is my product for my numerator and denominator. I got 625.5. In terms of sig figs, our molarities would be the only thing that we would look at. The 200 degrees Celsius doesn't matter because that wasn't used in any calculation. So I got 626, and again, don't worry about any units. Okay, one more type of problem. What if we're given the KEQ and asked to solve for one of the of the substance's concentration at equilibrium? Okay, so we're not gonna stop and write the KEQ expression for this one because it happens to be the very same reaction. Oops, it looks like I failed to include my little arrow there. Let me fix that real quick. Okay, there we go. Now the reaction looks right. So essentially what I'm going to do is I'm going to plug in these numbers. There's my KEQ, here's my nitrogen, here's my ammonia, and we're going to solve for the unknown concentration of H2. So I'm just going to go ahead and set that up. All right, so that's what my my equation is going to look like with everything plugged in. There's my KEQ. Notice, by the way, this is essentially the same KEQ that we just found because we're at the same temperature, right? It's the same reaction. We're at the same temperature, 200 degrees Celsius. So we got 626. This time they have 625. So it's essentially the same thing. Okay, so anyway, we're trying to solve for H2, and it is going to be cubed. So we'll deal with that probably last. What I want you to do right now is just go ahead and rearrange the equation to get H2 cubed by itself, and then we'll take the cube root of it to get the final answer. So go ahead and rearrange the equation to get H2 cubed by itself. Okay, to kind of show my steps here, I just cross multiplied, so I multiplied both sides by H2 cubed times 0.03. And so I got this, and then of course to get the H2 cubed by itself, we are going to divide both sides, right? So we're going to end up with, so we're going to divide by 625 times 0.030 on both sides. And that is going to give us H2 cubed equals 0.12 squared over 625 times 0.30. Go ahead and do that calculation real quick. Okay, so my top here, 0.12 squared is 0.0144. Bottom, we get 18.75. And when I divide top by bottom, I could put this in scientific. I'm just going to go ahead and leave it in regular notation, 0.000768. And then all we have to do then to find the concentration of hydrogen is take the cube root, right? So right now we have H2 concentration cubed equals 0.000768. So if I just go ahead and take the cube root of both sides, which actually you can do on your calculator. So I'm just going to hit, oops, I hit the wrong button. 0.000768, and then I'm going to hit the little cube root button, and I get concentration of H2 at equilibrium equals 0.0915, which it looks like 2 sig figs in my my concentrations to start with. So that's going to round to 2 sig figs there. So that would be how you would find a equilibrium concentration of a reactant or product if you know the KEQ already. All right, the other section that I asked you guys to look at was a bit about non-reversible reactions. We'll talk about this really quickly. It involves no calculation at all, just some concepts. So how do we know that a reaction will not reach equilibrium at all because it's a one-way reaction? The first way is very simple. A precipitate forms. So if I get an insoluble solid here on the product side, that silver chloride, and this is not silver chloride, this is like lead chloride or lead nitrate, or no, I'm sorry, lead chloride, lead iodide, something like that. It's lead. Um, but if I do get an insoluble solid here in solution, those ions are no longer available to react and go back and make the original reactants again. So that would be one reason that a reaction would not reach equilibrium, because it's one of its products is all locked up in the form of a precipitate and unable to go back in the reverse direction. Another reason would be if a gas forms and escapes. So the simple reaction of pouring a soda or opening a soda is just basically allowing some carbonic acid to decompose to make carbon dioxide and water. So it's this reaction, H2CO3 goes to H2O plus CO2, and since CO2 is a gas, and here, as you pour it in the glass, it's escaping, it's not going to be a reaction that can go back in the other direction. Now, of course, if you keep the cap on, and let's say you're taking the bottle out of the fridge and you drop the bottle on the floor and you see the fizzing happening inside the bottle, that reaction is going to return to equilibrium because the CO2 is not escaping. So that would be a case where you would draw a return arrow because you're not losing the CO2, so it's able to actually re-establish equilibrium. And it usually does so in just a couple of seconds. Although if you drop a bottle of soda, you might want to wait a few minutes rather than a couple of seconds just in case. And then the last reason that reactions don't go in reverse is if the products are much more stable than the reactants. They were a little bit more specific in the CK12 reading. They said if you form water. And that's a great point to make, I guess, because, like, for example, combustion is a great example of this. If you're forming water, water is super stable. So you're not going to get that reaction to go back in reverse. If you think about it in terms of a potential energy diagram, a combustion reaction looks like this. There's a huge difference in the potential energy of the products, which include water vapor, and CO2, which are both very stable, and the stability, or I should say the potential energy of the reactants. Like, for example, in this case, methane. Very unstable, very high potential energy. So the likelihood that you're going to get carbon dioxide and water vapor to collide and go back up this huge hill is essentially non-existent. So it's not a reversible reaction.